Everything in our universe, living or non-living matters, forces and interactions, are believed to be carried by some particles, which physicists have divided into a few categories. Together, they are known as the standard model of particle physics. This model is governed by some conservation principles and interactions, and the backbone of this model is quantum field theory. In this video, we will discuss how we categorize the fundamental particles in these categories. Remember, we will not go to the detailed discussion and discoveries made in this field. Rather, this is gonna be a quick revisit, so watch the video till end. Take any particle in the universe. It will come under any one of these two types, fermions and bosons. Fermions are the particles having odd half-integer spin, such as 1/2, 3/2, 5/2, etc. Whereas bosons have whole integer spin 0, 1, 2, 3 and so on. Also, two fermions can never situate in same quantum state, but bosons can do that. This is quite good, but in standard model, the classification is made in an alternative way. Fundamental particles are divided as matter particles and force-carrying particles. Matter particles are those that constitute matters, and force carriers are the particles which are exchanged during interaction between matter particles. As there are 4 fundamental forces, there should be 4 force-carrying particles. We will talk about this later on. In this image, the particles on the right side are force carriers. The left side particles, aka matter particles, are of two types, hadrons and leptons. Hadrons are composed of quarks, fundamental particles having fractional electronic charge. There are 3 generations of quarks, that is, total 6 quarks, with all of them having their antiparticles known as antiquarks. So there is up quark, down quark, charm, strange, top, bottom, with their increasing mass, with all the antiquarks corresponding to them. In the hadron family, the particles made with the 3 suitable quarks are known as baryons. There are many baryons found so far, but the most common are neutrons and protons, which makes the nucleus of an atom. There are also mesons, which are combinations of one quark and one antiquark, but they are highly unstable. Notice that baryons are made of 3 fermions, so their net spin is also odd half integer. But mesons have 2 opposite spin particles that cancel each other and the net spin becomes 0. So baryons are fermions, but mesons are bosons, although both are made of fermions. Now let's go to the leptons. Just like quarks, there are 3 generations of leptons with increasing mass: electrons, muons and tau, and all of them having their associated neutrino, electron neutrino, muon neutrino and tau neutrino, and these 6 having their antiparticles. Electron is the elementary particle that make up outer shell of atoms. Muons and tau break apart in electrons in a very short time period, and neutrinos only interact with weak force and hence very hard to detect. Remember, all the leptons are fermions. Now let's dive one step inward. Force carriers. There are 4 fundamental interactions: electromagnetic force carried by photons, strong force by gluons, and weak force by W and Z bosons. And yeah, there is gravity, but we didn't discover any particle for gravity till now. All the force carriers are bosons, and they don't have any antiparticle, because simply they are antiparticle of themselves. Lastly, we have got Higgs boson that gives mass to all particles. In quantum field theory, it is said that matters interact with Higgs field that gives them the mass. One final question remains. Is the standard model complete? Well, we don't know. We don't know if we can find graviton, the particle carrying gravity. We don't know if we can find the dark matter particle, aka WIMP, or we can find prions, which are particles smaller than quark. We simply don't know.